All right. All right, let's get started today. Friday. Remember, there's a quiz. If you haven't taken the quiz yet, there's a quiz due by midnight tonight, right? And then I also posted a homework yesterday. That will be due a week from yesterday, so Thursday of next week, right? Same time, 5 o'clock, all right? Also next week, there'll be a quiz that'll become available on Wednesday, right? Bright and early, 12 in the morning, 12:01 a.m. Wednesday morning, if you really want to get after it, right? And then it'll stay open until Friday, okay? So don't forget to do that next week. Don't forget that I will not be here next week, like physically in this classroom. So don't show up unless you want to, right? This classroom's available for an hour from 8 o'clock. So if you want to come in here and do homework, by all means. I doubt there'll be many people with you, but it's an option, okay? I will be posting lectures, so check out on D2L the announcements, right? There'll be early in the class, I set an announcement that gave a link to our YouTube channel, okay? You can go out there. There'll be 3 lectures out there. I'm not sure exactly when I'll get them. I'll get them out there before each of our Monday, Wednesday, and Friday lectures next week, okay? They might come all today. They might come trickle through the week. I'll try and throw an announcement out there when I get one out there, okay? So you can go out and watch them. What else? I think that's it. So to continue on, are there any questions? Questions? Okay. To continue on with what we were talking about on Wednesday, we started talking about indeterminate axial systems, okay? We have, right, more unknowns than we have equations of equilibrium. So when we set up our problem, free body diagram, right, we have more of our red arrows here, right, our unknowns versus our knowns. Those are our blue arrows, are our applied forces. All right. When we have more unknowns than we have equations of equilibrium, we need a process with which we can establish what these forces are. Well, if we have 3 equations of equilibrium and 6 unknowns, right, we need additional equations so that we can develop our unknowns, okay? So this solution process we start with is always with a free body diagram, right? We need to establish one that is that our problem is either determinate or indeterminate, okay? And how we develop these additional equations is we come up with relationships of deformation, right? Because we have our force deformation relationship equation where we relate the deformation of an axial loaded element to our force geometry, right? Length and area, and our modulus of elasticity. Okay. So depending on how that rod system is set up, right, we can come up with relationships. So if we have a rod system, we can come up with angular relationships of deformation, right? As each of those rods, 1 through 4, elongates, we can come up with a relationship of how does one rod elongate versus another. And if we know that deformation relationship, we can plug in our force deformation relationship equation, and we can relate forces to one another, okay? Deformation of all members is equal, right? If we had 2 elements that are in parallel, okay? If we have 2 members that are in parallel, right? They might be of different materials, and they're attached to the same end plates and beginning plates, right? If one deflects a certain amount, the other one's going to deflect the same amount. If we have a series of rods, right, at 2 fixed supports, if these 2 rods were connected, right, at a point, and we decided to add load at that point, and that point moves, well, the overall dimension is going to stay the same. And so we know the overall change in deformation has to be 0. So if we move to the right 1 unit, right, our second rod gets smaller by 1 unit, but our first rod has to get longer by 1 unit. And so our total deformation is 0. Once we know these relationships, we can plug in our force deformation relationship equation and come up with additional equations so we can solve for all our unknowns, okay? So this is an example we've got two rods, right? Just as the last one we just looked at in the previous page, right? We have a series multi-segment rod system. Areas they're giving us as 3,600 millimeters squared and 2,000 millimeters squared. They told us that our modulus of elasticity for our first rod is 200 gigapascals, and our second rod is 70 gigapascals. Well, that means our second rod, right, is about a third as stiff as our first rod. Then they said they're giving us some limiting stress, right? It says find the maximum force P without exceeding the stress in either rod. Well, the stress in our rods, they're telling us, need to be 160 megapascals in rod 1 and 120 megapascals in rod 2. So if we establish a free body diagram, first step in our process, right? Don't know if this is determinate or indeterminate, right? Just gonna break out the system, put in our known and unknown forces. Well, our known forces, right, are just really our force P, right? Or P over 2 times 2. Symmetrically loaded, so we really just have one axial load P acting at the center of our rods, or the center line of our rods. We have points A, B, and C. We need some sort of coordinate system. I'm going to say it's positive x to the right. We also know that we're going to have some unknown forces, right? We have these bolted end plates or flange plates at the ends of our rod segment, right, on the walls. We know that those aren't going to move. Well, if those don't move, but we're adding loads, we're going to have some sort of reaction, right? Some reaction at C, some reaction at A. I'm just putting them in a direction that I'm guessing that they're acting in, right? The math will work itself out for us on which direction they actually act. So if we sum forces about the x, right? That's really the only equation of equilibrium that we have, right? Some of the forces in the y, well, we don't have any forces in the y. Some of the forces in the z, no forces in the z. Some of the moments, well, all of these forces are coincident, right? They're all acting along the same line, so none of them have a moment arm. So none of those equations help us. So we get one equation of equilibrium, sum of the forces in the x. Well, I assumed that FC was off to the right, which is our positive, so it's positive. I'm going to subtract FA, because I assumed it went to the left. And then finally, I'm going to subtract P, because I also put it to the left, because we knew which direction P was acting, right? They give us what that direction is. Well, we have two unknowns, right? One equation of equilibrium. This problem is indeterminate, and it's indeterminate to the first degree. Right? We need one more equation, and we could solve for our forces, right? We need two equations for two unknowns. I'm going to make a substitution and say FC, I'm going to just call F2, right? That's the force in rod 2. If I were to just, we took this out of the supports, so really this is rod 2 on the right-hand side of our applied forces. This is rod 1. So really the internal force in rod 2 is FC, and the internal force in rod 1 is FA. Right? Well, if we follow our solution process for indeterminate systems, right, we need additional equations of equilibrium. Right? Based on that list in your notes, anybody come up with an equation that they would use to relate the deformation of our two rods in this system? Any ideas? Yeah? Yeah, exactly. right? The total deformation has to equal 0. We have fixed end supports. So we know that our behavior of our system needs to act something like this, right? If that plate moves to the right, because the end plates aren't moving, right? Member 2 is going to get smaller. Well, member 1 is going to get just as long, right? It's going to compensate for that loss of length in the second member. So if you add those together, we're going to get 0. Right? So essentially, whoops. This thing going on, fixed supports, got some load P, right? This right here is a constant. What does that mean? Well, the total system change in length, right, has to be that constant. That constant is 0. It's got to be 0 because it's not going to change length overall. Well, what does that mean? Well, if we were to rearrange this, we could say that delta 1 is the opposite of delta 2, right? We just took delta 2, subtracted it to the other side. We'd get delta 1 is negative delta 2. Well, when we use that, right, now we have this relationship of deformation between the two rods. Well, we also have the force relationship to deformation of each rod. Right, we have delta 1. Well, delta 1 is the same as saying the force in 1 times the length in 1 over the area of 1 times the modulus of elasticity of 1, right? Similarly, we have this same relationship with respect to member 2's cross-sectional, right? Geometry, material properties, and internal forces. Well, we have delta 1 equals negative delta 2. Well, we have delta 1 and delta 2 in terms of forces, right? And known other parameters. Well, I'm just going to make that substitution. I'm going to say delta total, right, is equal to 0. Well, that's F1, L1, A1, E1 plus F2, L2, A2, E2. Or if we rearranged it the way we had it, right, and then substituted or just rearranged as a whole for F2, right, one of the forces. This right here gives us an equation in terms of unknown forces, right? So this would be one equation with two unknowns. Right? This is our other equation with two unknowns. Right? We know FC is F2 and FA is F1. So now we have two equations and two unknowns. I'm going to solve this equation for one of my unknowns, negative F1, L1, A1, E1, multiplied by E2, A2 over L2. Right? Now that we know one force in terms of the other, based on our deformation relationship, we can substitute that force 2, right, back into our equilibrium. Equation that said our sum of our forces in the x equals 0, and that was negative F1, right, or F sub A plus F2 minus P. Well, if we take this, plug it into there, do some rearranging, we get P minus F1 minus F1, L1, A1, E1 times E2, A2 over L2. Could simplify this a little bit more, say, whoops, negative F1. I'm going to pull all the F1s out. L1 over L2, E2 over E1, and finally A2 over A1. All right. We know our applied load. Right. We could get our applied load based on knowing the force in one and our geometry of each of our rods, our material properties of each of our rods, and the cross-sectional area of each of our rods. Okay. Well, they didn't give us P, right? They said, what is our max P without exceeding the stress in either rod, right? Well, what is our equation for stress? Stress is force over area, right? It's never going to change. This is a safe space. You can be wrong. I can be wrong. I'm wrong all the time, okay? Stress is force over area, right? So they gave us stress. We know the cross-sectional area, right? The only thing in that equation we don't know is force, so I'm going to rearrange for force, right? I'm going to say, well, if we're looking at rod 1, right, the force in rod 1, well, that's going to be the stress that we are limited to in rod 1 times the area of rod 1. Okay. Well, if we look back up here, right, I conveniently rearrange this so that I could take this quantity, right, stress 1, area 1, and just plug it in for F1, right? Put it up there. And create an equation in doing so, right? So P equals negative stress 1, area 1, right? Or F1, that's all that is, F1, times that big glob of stuff. Something like that, right? It's A2 over E, yes, A2. Okay. Well, we know everything here. Know everything on the right-hand side. We can figure out now what force we can apply where we will not go beyond, right? We're going to be sitting right at the maximum stress in rod 1 or member 1. So let's plug that in. At this point, we got to start thinking about units, right? There's a lot of units going on in this equation on the right-hand side. We know what we want to get out is a force, right? So that's going to be in pounds, kips, in this case, newtons, right? Or kilonewtons. So we're in SI. So we just want to make sure we follow our units here. Well, they told us it was 160 megapascals, right? 160 megapascals, 200 gigapascals, and an area of 3,600 millimeters squared. Also, rod 1, right? The length of rod 1 is 1.8 meters. So we have 160 megapascals. Well, we know megapascals is Newton per millimeter squared. We know the area that we just said was 3,600 millimeters squared. Then we got this big mess of stuff. Well, we've got the length of rod 1 over rod 2. Well, it's 1.8 meters over 1.4 meters. And then we've got our E's. Well, we have 70 megapascals. That is the modulus for rod 2. Or, sorry, yeah. Thank you. Gigapascals. Gigapascals. And then finally the area, right? Again, whoops. Got to remember that it's area 2 over area 1, so it's 2,000 millimeters squared over 3,600 millimeters squared. Well, if we look here, right, all of our units cancel on our L's, A's, and E's. If we look over here, right, megapascals is a Newton per millimeter squared. Well, we had area in millimeters squared, okay? So we were able to cancel those out. So our answer we're going to get is saying P equals negative 720,000 newtons or negative 720 kilonewtons. Well, just like we did up here where we rearranged for an equation that related P with respect to the force in rod 1, we can do the exact same thing. Right, sum of the forces in the X equals 0 equals negative F1 plus F2 minus P, okay? And all the negative meant right here, right, is that our original assumption of direction is actually in the wrong direction, right? P is actually opposite with respect to the direction of force in rod 1, which if you can imagine, right, looking at this, we were looking at rod 1, right? If we apply the force P that heads this way, both of these reactions should have gone this way, right? So all that's saying is coming out negative is that the direction that we assumed is actually opposite of the actual direction relative to the applied load, okay? So that's why that's negative. So we have F1 now, based on this equation, right? F2, L2, E2, A2 times E1, A1 over L1, right? Just based on rearranging that equation. F2 is L2 over L1, E1, E2, A1, A2 plus 1. And plugging all that in, which I'm going to save you guys the pain of doing that. We get 1.2 million newtons, or 1,200 kilonewtons, right? It's positive. What does that mean? Well, the direction that we assumed in our initial free body diagram, all that means is that we assume the right direction. Okay. Based on this, if we put P to the left, that reaction at 2 is to the right. Okay. Based on this, right, they asked us for what's the maximum P that we could apply to reach our stress in each of our rods. Which out of these two, what would be our P that we would use? 720 kilonewtons, right? That is our limiting. That is our limiting applied load, right? If we started at 0, we started pushing and pushing and pushing and slowly increasing that load, well, at some point, right, we're going to hit the limit, and unfortunately, rod 1 is our limiting rod where we would hit the stress, right? We're going to hit 160 megapascals first in rod 1. Right? Essentially failing this member before we get rod 2 to its 120 megapascals. Okay. Which, looking at this, right, rod 1 is larger than rod 2. Okay. But it's the fact that rod 1 is stiffer, right, that really plays a huge role in the fact that as you push on it, it's going to attract load 3 times as fast as rod 2 would, right? Because it's stiffer. So for every 1 unit of deformation, you're going to get 3 times as much load in rod 1 as you would get in rod 2. Yeah?
So the only thing you change to get the different P besides all like basically all like stresses and stuff for the forces were the calculation for F1 and F2 right at the beginning of the stress and area for your P equation.
For the second rod?
Yeah, is that the only thing you changed is like right at the beginning? And then all the given information? You just get to put that back in the
Yes. So like you essentially are taking the exact same steps, which from this equation here, you would take our stress equation, right? Now we would plug in here, just like we did up there, where now we're going to have stress 2 times area 2. And then in that case, then now we have everything in this equation. And we would just plug it in, and that would limit our force to being at our maximum stress based on all of the geometric parameters, right? The area and length, and then our stiffnesses. That answer your question? Okay. All right. I'm going to go through another example here. We're going to do a kind of a rod, axial rod system. So assume we had a parallel running tracks, right? Suspended from the ceiling. The new Big Sky High School is going to have something like this, where you had a platform suspended by multiple rods, okay? And in this, we're applying a load P to the bottom of it. Maybe you're hanging a basketball hoop or something like that, right, in a gym situation. They tell us that all the bars are aluminum, right? So that they all have the same stiffness. They're 10,000 KSI. They all have the same diameter. They're 5/8 of an inch, okay, diameter. They're spaced at 72 inches, right, 6 feet on center. That load that we're applying is 5 feet, right, 60 inches from point B. And all of these rods are 90 inches tall, right, 7'6". Okay. For a load of P of 16,000 pounds, right, that'd be one hell of a basketball hoop. Right. They want us to determine what's the tension in each of our rods. Okay, 1, 2, and 3. And then on top of that, they want to find what's the vertical deflection of the rigid bar at B, right? B being that initial point, right? That far left point. So you can imagine, we start out with our free body diagram, right? We want to know internal forces. What's the tension force produced in each rod? Right? Well, we need to figure out what do we know and don't know about this system. Well, I'm going to essentially cut out, right, that bar. We really want to know the tension of the rod, so I want to cut out those rods. I'm going to cut those rods out. I'm going to establish my free body diagram, right? So we're going to have a point B. We know at the midpoint we have point D, and then at the far end we have point F. I want some sort of coordinate system, so I'm going to do positive X to the right, positive Y straight up. We've got some unknown forces acting on this bar, right? We're going to have some sort of force in each of our rods. Well, I'm assuming, just based on looking at this, if the load is downward, each of these rods should be pulling up on the bar to hold it up. Okay, so I'm going to assume that these things are in tension, pulling up on our bar. So we have F1, 2, and 3, right? Unknown forces, don't know what they are yet. We need some dimensions. Well, this we know is 72 inches. This we know is 72 inches. Well, we also have this known load, right? P, say it's 16,000 pounds, 16 kips. And we know that it is acting at 60 inches from point B. So we have a coordinate system. we've imposed our known and unknown forces, right? Unknown being everything in the rods, the known being our basketball hoop or that 16,000 pound point load, okay? And then we have coordinates, right? We need to establish direction, give ourselves our positives and negatives on our forces. So based on this free body diagram, what is one equation of equilibrium we could use? Some moments. Okay, that's a great one. If you're going to pick a point to some moments about, which one would it be?
B.
Sweet, that's exactly what I guessed. I like that. So we could sum the moments about B. Well, we know the sum of the moments equals 0. Well, we have F2, right? If we started at the left-hand side, right, we're summing the moments about B. Well, force 1 has no moment arm, right? So there's going to be no moment associated with force 1. Knocks it out of the equation there. Force 2 does. Right-hand rule, right? Curling your fingers, thumbs out of the page. It's going to be positive. So F2 times its moment arm. Well, I'm going to keep it in our numeric or our alphanumeric form, right? So A. We know that it's 72 inches, but I'm going to keep it at A for now. Secondly, we've got force 3. Same thing, except for now it has twice the moment arm, right? Or 2A. Finally, we have our applied load. Well, it's going to have a negative right-hand rule, right? And its moment arm is its distance B, right? The perpendicular distance between the point that you are summing moments about to the applied force. So we have one equation of equilibrium. What is another equation of equilibrium we can use for this? Forces in the Y. I like that one. Some of the forces in the Y direction, well, we have all of our applied forces, F1, F2, F3, all assumed in the positive direction based on our coordinate system. And finally, we have our applied load, right? P, we know that what that is. It's acting downward, so we have a negative P. Are there any other equations of equilibrium we can use that are useful? Maybe? No? Shaking your head, no? There isn't, right? We're done. We've got two equations of equilibrium that are applicable here. Well, we have three unknowns. So again, first degree, indeterminate. First degree indeterminate. What do we do now? Right. We come up with that relationship for deformation. Yes.
So in your first equation, you have three unknowns, right? In the second one, you have four. So which one would you use to?
So yes. So I guess P is known, right? They're giving it to us as 16 kips.
Oh, okay.
So even though, yes, I put it in here as P, I'm just doing it so we can see, alphabetically, right, variable-wise, where each thing is landing in their contribution. So you could say that the first equation has two unknowns, the second equation has three unknowns, but overall, from a system of equations standpoint, right, we have two equations, but we have three unknowns as part of those two equations, and so we cannot solve, right? We could again, like in some of the moments, right, we could solve this equation. We could say F2 equals some blob, right? That's a function of F3 and P and A's, right? Well, if we took that F2 that we did then just solved for F3, right? We plug it into here, so now we have one equation with F1 and F3. We can't solve that, right? But yeah, P is known, and our unknowns are F1, F2, and F3. We only have two equations, so we cannot solve for those unknowns. And so we need to figure out what's going on with respect to deformation, right? We really just need additional equations that relate forces, right? That's all we're trying to do. And the benefit to us is that we have an equation that relates deformation to forces. And so we need to come up with a relationship of what's going on with respect to deformation. So if I looked at that free body diagram, and really if I looked at the original problem, right? If we pulled down P assuming that that bar is rigid, right? It's not going to deflect and bend based on that 16,000 pound point load. It's going to be a straight line, right? When it starts, it's going to be flat, something like that. And when we're done applying that point load, right, it's going to rotate, right, and deflect, something like that, right? The P is not symmetrical. So you can imagine P is going to influence rods 1 and 2 more than rod 3. So those two rods are going to deflect more. It's going to do some sort of rotation. This would be what we would call the deflection at 1, deflection at 2, and deflection at 3, right? Each of our 3 rods, they're all going to deflect. This distance is all the same, right? This is A and A. Well, if we have a straight line that connects 1 and 3, okay, straight line that connects 1 and 3, and our distance between rod 2 and rod 3 and rod 2 and rod 1 are the same, right? That means we're at the midpoint. We're always going to be at the midpoint of this straight line. Anybody think about what we could say about the displacement of rod 2 in terms of rod 1 and 3?
Proportional.
It is proportional, right? I might say it's the average, right? If this was always a straight line, right? No matter how far this thing deflect, right? Because the fact that rod 2 is halfway between rods 1 and rods 3, this is always, I almost just wrote it on my paper, right? Rod 2 is always going to be halfway the displacement between rods 1 and rod 3. Everyone believe me there? So in order to get that, I'm just going to take the average, right? Add up the displacement of rod 1 to rod 3 divided by 2. Well, if we want to get rid of some of the fractions, right, we could just say rod 1 plus rod 3 displacements equals 2 times the displacements of rod 2, right? Just essentially taking the 2, multiplying it to the other side. We get 2 times the displacement of rod 2 equals the displacement of rod 1 plus the displacement of rod 3. Everyone trust me there? Yeah? Okay. Well, just like we did in the last example, right? Next step is, well, we have this deformation relationship. We know we want to get forces, right? We need a relationship of forces so we can have another equation that we can use to get 3 equations, 3 unknowns. Well, we know displacement of 1 is F1, L1, A1, E1, oh. Right, we have these 3 relationships that give us the displacement of each of our rod in terms of the geometry of our rod, our material properties of our rod, and the internal force in our rod. Okay. Well, we have this substitution we need to do, right? We have rod 1 displacement plus the rod 3 displacement equals 2 times the displacement of rod 2. What do we do here? Well, we just substitute in all of our deformation equations into that equation, right? So now we get this F1, L1, A1, E1 plus F3, L3, A3, E3. Well, that's 2 times F2, L2, A2, E2, right? Well, lucky for us, L1, L2, L3, all the same, right? They were 90 inches long. A1, A2, A3, all the same, right? They're all 0.625 or 5/8 of an inch in diameter. And they're all made of aluminum, right? E1, E2, E3 are all the same. Well, what does that mean? Well, that means we can just pull out all of those, right? And our equation then becomes F1 plus F3 equals 2 times F2. All of that substitution, all it was for was we really wanted this, right? We want an equation that gives us forces in each of our rods and a relationship between those forces so that we can use, right, our equations of equilibrium. We have this sum of the forces in the y. Well, that is F1, F2, F3 minus P. We had some of the moments, right, about point B, or the left-hand side of our rigid bar, F2A plus F3 times 2A minus P times its moment arm, which was B. Right, so this is our deformation relationship, and this was our equilibrium relationships, right? Well, now we have 3 equations and 3 unknowns. Wow, I need to learn how to spell. Knowns. Right? We can solve this. Well, I'm going to start by using the sum of the forces in the y, okay? Could do this in a number of ways. Right? Sum of the forces in the y. What do we do here? Well, we could say that we could rearrange this and say our deformation equation, right? F1 plus F3 is 2F2. Well, if we look at this equation, right, sum of the forces in the y, we have F1 plus F3, right? So we really have 2 F2s. So this becomes 2F2 plus F2 minus P, or 3FP, right? So sum of the forces equals 0, right? 2F2 plus F2 minus P equals 0. Well, that means F2 equals P over 3, right? Well, they gave us P, that was 16 kips. I'm going to divide that by 3. So we can say F2 equals 5.33 kips. F2, 5.33 kips. Well, out of our 3 equations we have, yeah.
Can you explain how we only got? Oh wait, never mind. I see.
Got it?
Got it.
Okay. You don't have to have it, you can ask.
No, I got it. I was wondering how we got the only 1 2F2, but it's the F1 plus the F3. We just
Yes.
substitute. Yeah.
Yep. So we took the first equation, just plugged it into the second equation, got rid of 1 and 3, got 2F2 out of it. So now we have 3F2, right? We have F2F2 plus F2 minus P. We get F2 is P over 3, or third, right? That's 5.33 kips. Well, now that we have F2, the equation that would be nice up there, right, is the sum of the moments about B. Well, it's only a function of F2 and F3. Well, if we know what F2 is now, we can plug it into that equation and figure out what F3 is. So sum of the moments about B equals 0. Well, now we have, right, I'm going to say P over 3 times A, right? That's F2, plus F3 times 2A minus P times B. Well, if we plug in all of that stuff, right? A was 72 inches. B was 60 inches. P is 16 kips. We can just solve this for F3, and we're going to get that F3 is 4 kips. Well, that's easy enough. Well, now we know F2 and F3. Well, we have our deformation equation, or even our sum of the forces in the Y equation, has all 3 of our unknowns, so we can plug in the values for F2 and F3 and figure out our last unknown, which is F1. So I'm going to say F1 plus F3 equals 2F2, right? Or F1, if we rearrange this, is 2F2 minus F3, or 2 times 5.33 kips minus 4 kips. That means F1 equals 6.67 kips. Right, so those are our answers to part 1, right? What were our internal forces? Well, they asked for one last thing. They said, what is the displacement at B? Well, the displacement at B is going to be the displacement or change in length of rod 1, right? Well, we know the equation of displacement at B is the displacement at 1, which is F1, L1, A1, E1, right? Well, F1 is 6.67 kips. L1 is 90 inches. A1 is pi over 4 times 0.625 squared, right? They gave us the diameter, the area of a circle given the diameter is pi over 4d squared. And then our modulus of elasticity, they told us it was aluminum, 10,000 KSI. Everything in this equation is kips and inches, right? So our inches squared cancel out of the denominator. Our kip in the denominator cancels with our kip in the numerator. And we end up just with inches, right? The inches off the 90. So we could say the displacement at B is 0.1225 inches. Yes?
Why is the displacement of B the same as the displacement of 1?
Because, right, B is at the end of rod 1.
Oh, I'm sorry, I was looking at the distance being.
Oh, yeah. Sorry. Yep.
Okay, yes.
Yep. That's why. Any other questions? All right. Yeah. What do you want?
So, on a test, if you have the 3 equations and the 3 unknowns, can we just plug that in our calculator? Or do you want us to show
You can plug it in your calculator. I would probably just set up the 3, and then you can make the jump, right? You don't have to like solve for one into the other and then back and forth. But if you had all 3 equations written out correctly, and then you get the 3 answers correctly, I'd say you're good. The only reason why I propose doing more work on paper is for partial credit, right? In case you did make a mistake somewhere. It's easier to follow.